From the Library of Congress in Washington, D.C.
Good morning and welcome to the 6th of our 8 lectures this year in our NASA series. We've got a couple of exciting ones coming up, but I'm not going to tell you about them because we have a little sheet outside on the table that tells you what they are. I'm Stephanie Marcus from the Science, Technology, and Business Division, and Sean Bryant and I coordinate this series, and it's our 10th year, so we're having a great time and we're never going to stop. I imagine nobody here today is too pleased with the weather we're having, but our speaker, Alex Young, is going to tell us about the really nasty weather you might encounter when you book your trip to Mars. Dr. Young's educational background includes a BS in physics from Florida State University, a master's in physics from the University of New Hampshire, and also his PhD in physics is from the University of New Hampshire. After grad school, he came to NASA at some point and was a solar astrophysicist and worked on the NASA European Space Agency SOHO mission. I love the way they name these missions. They're always pretty cool. The SOHO was the Solar and Heliospheric Observatory. His current position is Associate Director for Science in the Heliophysics Science Division at NASA Goddard. And he is responsible there for overseeing and coordinating the education and public outreach team for the division. But he says now they pretty much reach out for all of the space sciences divisions as well as his. But he continues his research in the science of space weather, and he's very much into solar image processing. Besides giving lectures like this one and doing TV and radio interviews and also Discovery Channel documentaries, Dr. Young has established a website, thesuntoday.org, and it has a companion Facebook page, and he's also on Twitter and YouTube, so check him out. The Sun Today. And now let's get on with the Space Weather Report, and welcome Dr. Young.
All right, thank you.
You're welcome.
Thank you, everyone. I have to say it's going to be a little bit difficult for me. I'm used to moving around. I don't really stand still when I give talks, but I was told that because they're doing the webcast, I have to force any urge to get out and express myself. So hopefully I won't knock anything over because I tend to talk about big explosions and use my arms. And but I want to give you a little bit of perspective into weather, not here on Earth, but weather in space, in an area we call space weather. My area of research is in solar astrophysics. I've, for about 12 years, studied large explosions on the sun, other stars, as well as their impact through the solar system and here on Earth. And then after that, as was mentioned, I got more involved in education and public outreach, but I still do some research. Right now, for example, I'm looking at the impacts of space weather on data centers, working with, for example, Google, to see what sort of possible impacts it could have here on the ground. But what I want to do today is just give you a little bit of an overview and a look at the whole area of space weather, where the sun comes into play, and what sort of implications that has for the Earth, for us here on Earth, but in addition, through the entire solar system. Because one of the things that's really important for NASA, in addition to just human spaceflight, is the fact that we have a lot of technology scattered through the solar system, because we're interested in looking at all sorts of things, everything from planets to comets and asteroids. And the impacts of space weather are not just here on Earth, but also on the technology that we have throughout the solar system. And so that's one of the areas that's very important to NASA. But to start off, so I want you to indulge me for a second and think a little bit about what is it you think about the sun. You know, what is your thought of the sun on a daily basis? Close your eyes, maybe, and when you think about the sun, maybe you think about a sunrise or sunset, or what's your sort of general thoughts about it? Now, this may be the kind of image that comes to mind. Or even, let's say you put a camera up, you might get something like this. There's all kinds of cool things you can see. Sometimes you see halos around the sun from ice crystals, that sort of stuff. But also you may think about it as, let's say you have a telescope and you do some safe solar viewing with the appropriate kind of filter, look at the sun. You may see something a little bit like this. Still, it's not really that exciting. It's kind of boring, it's sort of a yellow disk. If you look at it long enough, you'll notice there are things that are moving across the surface. These are called sunspots. You can sometimes see them with the naked eye with solar glasses like the ones that are outside. If you look up at the sun, when there's a large enough sunspot, you can see these. To give you some perspective, this is about the size of the Earth, that sunspot right there. Okay, that's a decent sized sunspot, not too big, not too small. The other thing you notice here, which you don't necessarily notice maybe on a daily basis, is we see the sun move through the sky, but you may not even think about the fact that it rotates. Just like other planets, the sun is spinning. We're rotating around it, but it is also spinning. Now, there is one time when you can really see something more interesting on the sun, and that is during a total solar eclipse. So the first time that humans realized that there's a little bit more interesting stuff going on was not just these sunspots, but something like this. Okay, so here the moon has blocked out the sun almost completely, and you will see there's a little spot there. This actually doesn't quite show up, but this is in fact red. If you look at that little piece that's sticking out on the edge there is red. You see all this structure. Now, this is cheating a little bit. They've taken a couple images and overlaid them. You will see this wispy structure if you look at it from the ground. You don't quite see this fine detail, but you will see this sort of wispy halo structure that comes out of the sun during this brief period we call totality, when it is in fact safe to look at the sun. If you are I'm sure you've all heard you should never look at the sun without the appropriate equipment or glasses or filters if you're using a telescope. But in fact, during a total solar eclipse, usually a period of somewhere between a couple of minutes, maybe the longest one recently was about 7 minutes, it is safe to look at the sun. And this is something you would see only with your naked eye. You would not see this if you use those solar glasses. They would completely block this out. As a matter of fact, you wouldn't see anything with the solar glasses on during the total solar eclipse. But you see all this structure, and this was sort of the first indication that there's something interesting going on. The sun is a little bit more exciting than this sort of this yellow disk in the sky. But if we step outside of our atmosphere, let's go up into space, use a spacecraft and telescopes in space to look at the sun, we get a different perspective. This is what we see. This is a lot different than what it looks like on the ground. Now, in this case, you see there's all of this amazing structure, and everywhere you look on the sun, there's something happening. From the tiniest scales you can see to things almost the size of the entire sun. You see when there's this flash, you'll see this flash of light when it recycles, and you see this structure that looks like it's moving across the whole sun. That is in fact a wave. There is an explosion that sends a wave across the entire surface of the sun, traveling several million miles an hour. That's a result of that explosion you saw. So that flash you saw was a solar flare, an extremely intense release of energy, of light over the entire spectrum. Okay, not just the visible spectrum that we see, but everything from infrared to radio to microwave, or in the other direction, ultraviolet, extreme ultraviolet, X-rays, even gamma rays. So the sun puts out energy through the entire electromagnetic spectrum. So that was a solar flare. But you also see all of this stuff moving and wiggling around, and you see right here something moves. There's a big structure that actually erupts from the sun. We're going to look at it shortly from a different perspective. It's kind of hard to see from this perspective, but you're actually going to see things flying away from the sun. What's happening here is not only is the sun exploding and releasing this light, this solar flare, but it's actually throwing off billions of tons of its material at many millions of miles an hour. It's traveling away from the sun through the solar system, sometimes to us, sometimes to other parts. The other thing, and this is where I tend to want to run out and sort of show you with my arms, I'll try to do this without going anywhere, but when that big blast of material comes away from the sun, it's traveling so fast it's scooping up everything in front of it. Because space is actually not empty, and I'll talk more about that. There's particles and there's material out there, and it gets scooped up like a snowplow and pushed incredibly fast. And there's also this huge blast of particles that get accelerated to near the speed of light. And I'll show you what that looks like shortly. But those are three parts of space weather. So there's the flash, the solar flare. Enough energy is released in a moderate-sized solar flare to power the world, the entire globe, for 100,000 years. Okay. And now if you want to get in terms of explosions, that's billions of atomic bombs, of World War II-sized atomic bombs. That's the amount of energy released in that. The amount of energy released in that stuff that's thrown out, we call that a coronal mass ejection. The outer atmosphere of the sun is called the corona, and this is just mass, stuff that's thrown out. It's not just material, but it's also magnetic fields, and I'll talk about that soon because that's a very key feature, magnetic fields. That's coronal mass ejection, has almost as much, or if not more energy sometimes than that flare. And then those particles that are accelerated away. So those are three parts of space weather, and we'll talk in a little bit about what the implications of those are, what they do. But why do we want to look at the sun from space? Well, you can see here there's an awful lot of structure you see that's happening. It turns out that when you go into space and you use a set of telescopes that look at different wavelengths of light, you can see the sun is vastly different depending on the wavelength of light you look at. So this yellow part is the visible sun. You see the sunspot. But as we move around, we go from ultraviolet to extreme ultraviolet to near X-ray energies. And you see, as you're cycling around, you see that depending on the wavelength of light, what you see is very different. Now, these colors are artificial because really we're looking at the part of light that's not visible. So color, there really is no color. They're actually black and white or grayscale images, but we've colored them because that tells us, as a scientist, I can look at any one of those colors and I know which wavelength of light that is. And why is that important? Because each one of these not only shows us different structures, but it in fact is showing us different temperatures of the sun. So the surface of the sun here is about 10,000 degrees. But as we move up, this is about 20,000. This is somewhere between 40 to 80,000. This is 1,000,000. This is 10 million degrees. So as you move out from the surface of the sun, the visible surface, you're actually going up in temperature. So you're also moving higher in the atmosphere. Okay. So this outer part, all of this stuff here, this is the corona, the part that you saw during the total solar eclipse. But now we're seeing all of those wispy structures in detail. You're seeing it actually connect back to the sun. Because before you were just seeing not the disk of the sun, but sort of the outer atmosphere. Okay, so that's why we go out in space. Because, for example, watch that sunspot and see how it changes as you move around. It actually gets brighter right here. It's brighter there. Here's another thing. you'll notice these loop-like structures. And we're going to come back to that. But in fact, those are related to these magnetic fields that I was talking about. So let's look at some detail in these different wavelengths. I'm going to pick a couple of them. One that's going to show us the 1,000,000 degrees and one that's going to show us about the 80,000, 100,000 degrees. So this is roughly 1,000,000 degrees. All of these bright patches are where the sunspots are. We're now looking in extreme ultraviolet, not visible light. And where they were dark in visible light, they're actually very bright because they're very hot. And so the material is glowing. It is so hot that it's glowing, millions of degrees. And then you see these loops. Those are magnetic fields. Now, magnetic fields, the invisible force that you feel when you take a magnet and stick it on your refrigerator and it holds it to the refrigerator, that's an invisible force. But here, we're not actually seeing the magnetic fields directly. We're seeing the material follow along the magnetic fields. The magnetic fields are invisible, but the material the sun is made up of is electromagnetic. It responds to magnetic fields. And so the magnetic fields collect that stuff, that material on the sun, and it traces them out. And so you can see them. Normally you wouldn't be able to see them. Now, just so you know, that material is called a plasma. We won't go into the details of that, but that's actually what happens when you heat something up to super, super high temperatures. It actually goes from, if you take, for example, water, starts off as ice when it's very cold, that's a solid. You heat it up a little bit, turns into a liquid. Heat it up even more, turns into a gas. Well, if you heat it up a lot more, it actually turns into a plasma. And that's the fourth state of matter. So there are 4 states of matter. We here on Earth live in an environment where plasma is actually rare, but in fact, through the universe, all of the visible material that we see is mostly plasma. Plasma is the predominant form of matter in the universe, visible matter that we see. That's not getting into the kind of crazy stuff like dark matter. But the visible matter that we see, stars and nebulas and galaxies and all that, it's all plasma. And that's what the sun is made up of. And the cool thing about a plasma, it acts like a liquid in a gas, but it's electromagnetic. It responds to electricity and magnetism, and that's really a key feature to it. And here, it acts as a tracer for these magnetic fields. Let's look at slightly cooler temperature, slightly lower down in the atmosphere. This is about 100,000, somewhere between 40 to 100,000 degrees. And here, you're seeing something similar to those loops that you saw, but what you're seeing here is material that's being supported above the surface of the sun by magnetic fields. So if you remember back when I mentioned during that total solar eclipse, up at the very top, there's this little stuff sticking out, and I said, actually, it's really red, it's kind of hard to see. This is the material. That's actually why they chose to color this red. This is a false color, but this is the same material shown in a different wavelength. And it is, in fact, red in visible light. It's called a prominence. And that's something you can see during a total solar eclipse. But now you can also see when we look at the sun from space. Again, here is a sunspot. And you see there these little tiny loops that are connecting the sunspots. So I won't go into too much detail, but the thing to think about sunspots, now, if you're at all familiar with the idea of a bar magnet, okay, have you ever seen a bar magnet, or even seen maybe in a class where you take a bar magnet and you put it next to some iron filings and it sort of traces out these invisible lines? That's really what's happening when you saw those loops. Same sort of principle. And a magnet, like a bar magnet, is a type of magnet that's a very simple structure, and it has a positive or a negative. It has a north or a south, depending on how you want to label it. And so the magnetic field lines go from one pole, plus or north, to the other pole, minus or south. And the Earth is the same way. You could think of the Earth as a sort of a bar magnet. It has a north pole and a south pole that's where it spins, but it also has a magnetic pole. And so the magnetic field lines go from one pole to the other. They connect them. And that's why you see these loops, because the sunspots are actually connected. One sunspot has a magnetic field line that's going to another sunspot. And they're almost like bar magnets on the side. So on the surface, you'll see a field, magnetic fields do like this and make these loops that you see coming out of the sun. And the reason that I wanted to bring that up is that is the driver of all of this energy that's coming away from the sun. It's magnetic fields. I'm going to show you a cartoon animation to give you some more detail of what's happening. But magnetic fields are kind of like rubber bands. They have tension, they have pressure. You take a rubber band, you take it, twist it, twist it, twist it, it's going to start to knot up. I actually used to give the analogy of phone cords, but then nobody knows that at a certain age, nobody knows what a phone cord is anymore. But we all remember when we had long phone cords, and as over time they would get all knotted up and become very difficult. Well, that's actually a similar sort of thing. So these magnetic fields on the sun are getting all twisted. So when you saw those sunspots moving across the sun, as they move, they actually get all twisted and knotted up. And if they get knotted up enough, you take a rubber band and you twist it and twist it and twist it, eventually it's going to pop. That energy's got to go somewhere. It can only hold so much. Magnetic fields are very similar in that way. As they get twisted and they build up energy, at some point, that energy's got to go somewhere. And what happens? That energy is released explosively, and bam, you see the solar flare and you see all that material come flying away. So that's what's happening when we have those eruptions on the sun. They're releasing this magnetic energy that's getting built up as the magnetic fields are getting all twisted and knotted. So I love this little, this actually got cut off because I had to change the aspect ratio of the talk, but I love this little cartoon. Basically it says, an increase in sunspots is an indicator of potentially dangerous solar activity. And then at the very end, the guy looks at it and says, I don't like the looks of this. So it's actually not so far from the truth. As you start to see more sunspots, bigger sunspots, very complicated sunspots, that means they have more energy built up inside of them and more potential to explode. And in fact, we see the number of sunspots over time goes up and down. Goes from very low number of sunspots to high number back down to low, roughly every 11 years. From low, high to low is roughly every 11 years. Sometimes it's shorter, maybe 10 and a half, 10, sometimes it's a little bit longer, but that's called the solar cycle, solar activity cycle. And people have been watching sunspots since the mid to early 1700s. Actually, they've been watching them much longer than that. They've been watching them for hundreds, potentially thousands of years, but we've been recording them. In Europe, they started recording them back in the early 1700s. And though the data got better over time, they did a pretty good job, and they've kept really decent records. And we can go back and we can see this up and down. We see some peaks are higher. You know, one solar cycle may be higher than the next one, a little bit lower. Some are a little bit longer, a little bit shorter. So as a matter of fact, right now we're in what we call, since we started numbering them, we're in cycle 24. And we're coming down off the peak. Somewhere around 2012, 2013 was the peak of the current cycle, 24. And this cycle turns out to be the smallest cycle in 100 years. So it's a relatively small cycle. But we still see solar activity. It's just compared to the previous one. And they go up and down. Sometimes we see a big one and then another big one and another big one and then a little bit smaller one. We don't really have a good handle of what pattern exists there. You're going to hear in the news every so often somebody's going to say, we're going to go into this next great solar minimum and everything is going to freeze up and the sun's doing this and that. Well, the reality is they don't really know what they're talking about because nobody knows, because the sun's been doing this for billions of years and we've only been watching it for a couple hundred years in that kind of detail. So there's no way we can truly understand what that pattern is yet. We get a little bit of a handle on it and we start trying to put some physics in, but we really don't understand that too well. Now, I'm going to show you a couple of quick examples of sunspots. This is zooming in with a very high resolution telescope. It happened to be one that I worked for in Japan called Hinode. And just to give you some size scale again, so those little dimples that you see wiggling, okay, that's real. Turns out that the energy from inside the sun moves to the surface, and when it gets close to the surface, it actually does what's called a convection cell. Just like boiling water, the energy rises to the surface, releases, cools back down, and it makes these what we call convection cells, these bubbles. So you see those little wiggles, those are real. And they're all about the size of Texas, just to give you some scale. So that's a sunspot. You saw this flash there. There was actually a visible flash. That actually is an indication it was a very strong solar flare. We don't generally see solar flares very well in visible light. This is visible light. So when you see that flash over it, that actually means it's pretty big. Here's another idea of the scale of sunspots. Again, you see these sunspots are very complicated. They're messy. And that's actually an indication that there's energy. There's energy stored up in them. When you see a nice, simple, round sunspot, it's boring. There's really not much to it. It means there's not a lot of energy. But as they start to get elongated and get kind of gnarly and broken up, that's actually a sign of complexity, and that means there's energy there. Now, I mentioned that one of the keys is magnetic fields, but there's another key about the energy that's stored up in the sun and what creates the dynamics that makes space weather. And it's something, I'm going to show you a cartoon animation, but it's something called differential rotation. So think for a second about planets like Jupiter, Saturn, the gas giants. Okay, these are not solid planets. When they rotate faster near as they get towards the equator, they rotate faster. As you move towards the poles, they rotate slower. That's why you see those bands, for example, because they're not solid. Well, the sun is not solid. The sun is a plasma, as I mentioned. And so that means that it doesn't rotate at the same rate when you're at the equator versus the poles. So it's a plasma. Plasmas are attracted to electricity and magnetism. So what happens is it means that when this plasma moves, it drags magnetic fields with it. Okay? So they're connected. They're coupled to each other. Now, the sun, in its simplest state, is also like the Earth. It's like a giant bar magnet. So it has magnetic fields that go from north to south, south to north, through it. So they're kind of this way. Now, watch this little animation. So you see the magnetic fields are going to start off up and down, but the equator's moving faster, and the plasma drags the magnetic field. So it drags the middle part faster. So inside the sun, the magnetic fields are getting all twisted up. So this is, you're actually looking inside. So you see how they get all knotted and they start popping through the surface? That's the sunspots. That's where the sunspots are. The magnetic fields are getting twisted up. They're rising up from underneath and they're popping through the visible surface, and that's a sunspot. So I'm going to show you another animation from a different perspective to show you what I'm talking about. Whoops. Let's see if this will go. Go. Well, it's supposed to. There we go. Okay. So there are the sunspots, and the magnetic field's coming through it. So from underneath, the magnetic fields that have gotten twisted start popping through the surface. And where they pop through, they suppress heat. So that means that they look dark. They're not actually dark, but they're dark compared to what's around them. And then eventually you see they get so knotted that they flash, they're releasing energy. That flash was the solar flare, and then you saw this little blob of stuff coming off the top. That's the coronal mass ejection. So I'll let this run through one more time. So they're popping through, they're getting pushed together, and then all of a sudden, there goes a piece of it and solar material flying away. Okay, so that's an animation of these complex eruptions. So here's sort of a static graphic. Now, for the moment, ignore the Earth, and of course this is not to scale, but ignore the Earth on the right. But what I want you to see is, again, these are the three parts. So there's actually a flash here, there's a brightening, that's the flare. All this stuff here is the CME, the coronal mass ejection. But remember, it's pushing stuff in front of it. It's actually creating what's called a shock wave. Just like a sonic boom, when an aircraft travels faster than the speed of sound, it actually creates this shock in front of it. That actually makes the noise, the boom. There's a shock here. So here is the shock wave in front, and those are those particles that I mentioned. I'm going to show you what those particles actually look like shortly, but those are again the sort of three parts of space weather: the flare, the release of light, the stuff, the material and magnetic field, the coronal mass ejection, and then all of the things that plows ahead of it, the things that pushes ahead of it, which are these particles. So the sun is always spitting stuff out. It has these big explosions, but also there is a constant stream of solar particles. So as I mentioned, as you move up in the solar atmosphere, it's getting hotter and hotter, and it is literally boiling off. It is escaping. It's so much energy that material from the sun escapes into space, and it is streaming away from the sun all the time, and it fills the entire solar system. It's called the solar wind. So there's sort of this background material that's always streaming away, and then these big explosions are like waves on top of the ocean. You know, the ocean, there's sort of this background ocean that's always there. And then you have these huge explosions which are releasing additional material on top of that, kind of riding on top of this solar wind that's always moving away from the sun. So that solar wind is always moving away, sort of ebb and flow, and we see that in our entire solar system. In fact, all of that material streams out way past the farthest planets in the solar system and creates this bubble around the solar system called the heliosphere. It's kind of the realm of influence of the sun. And here's a little animation of what that looks like. So you see the solar system is actually kind of small in there. There's this big bubble. Here are all these particles streaming away from the sun, and as solar activity goes up and down, that bubble expands and contracts. So this expansion and contraction is on the order of years. It's moving out, coming back in, and the reason you see this sort of elongated thing here is because this whole structure, the whole solar system, is traveling through the galaxy. And so you can think of it like a ship traveling through water, and it leaves this wake around it. And as a matter of fact, we've looked at other star systems with the Hubble Space Telescope, and we see this exact thing. We call those astrospheres. We see this kind of teardrop structure that's the bubble of a star traveling through the galaxy. That's why it's not just a perfect circle. You see this stuff coming out this way. We're going to see the same effect with the Earth. The Earth actually has the similar sort of structure called the magnetosphere as it's traveling through the solar system. And I'm going to show you what that looks like. But the key here is really that space is not empty. We're living inside of this environment that fills the whole solar system that's created by the sun. So there was an explosion there. Now we're moving away. There's the solar wind, these particles that are always there. But then there was an explosion, and there's going to be this blast of material. It's like driving into a blinding rainstorm. Now, these particles you're seeing, this visualization is actually based on real data. This is not an animation. This is real data. So there's the blob of stuff that is the coronal mass ejection traveling through space. Now, it's about to hit Venus. So those particles, the CME, coronal mass ejection, stuff also with magnetic field, is hitting Venus. Now notice it's sort of hitting Venus directly on. And I'm going to go back to that point. Now we're getting to the Earth. Now notice the particles. They're kind of moving around the Earth. See, some of them are kind of deflected here, above and below. And the reason is because the Earth has a magnetic field. Venus does not have a magnetic field, and that's why the particles were hitting Venus directly. Because these particles, this stuff from the sun, is electromagnetic in nature. It responds to electricity and magnetism. So the Earth's magnetic field is deflecting that. And actually, there's a cool animation. I don't want to go into it, but I was supposed to cut that off. But what I wanted to just point out is the Earth has a magnetic field, just like the sun does. It's kind of a bar magnet. It's a little more complicated. So all of this stuff coming off the sun is interacting with the Earth's magnetic field. In this case, it's deflected by it. And it actually creates this similar kind of teardropped, stretched bubble structure that I was talking about for the heliosphere. And we call that the magnetosphere. And so what happens when all that stuff interacts with the Earth's magnetic field? You get this. You get all of this stuff. This is the aurora. Sometimes called the northern or southern lights. In this case, we're actually looking at the southern lights because this is the International Space Station traveling over the Indian Ocean. But you see all of that crazy dynamic structure. That's because there are particles interacting with the Earth's magnetic field. In fact, those particles are hitting the atmosphere of the Earth. They're hitting oxygen and nitrogen, and they're exciting those elements and causing them to glow in greens, blues, sometimes red. So it depends on which element. It also depends on how high up they are. So what's really happening there? Okay, what's happening? So I mentioned that the Earth has a magnetic field. It's kind of like a bar magnet, but it's a little more complicated than that. But remember, all this stuff is coming off the sun. It's interacting with the magnetic field, and it stretches the Earth's magnetic field from this kind of spherical structure into this long, elongated thing. So I'm going to show you another computer visualization. This is real data connected with a computer model showing the magnetic field of the Earth to show you what's happening. So we're looking from the side. So you see, in this case, the sun is actually over here to the left. So there's stuff traveling, hitting. You see that starts off, it's almost kind of a little bit more symmetric, but it's dragging it all out this way. But when you see that blast that's hitting and pulling everything, that's the coronal mass ejection. That's the CME, that billions of tons of material slamming into the Earth's magnetosphere. Now this case, we're actually looking at data that was taken from an event that went off to the side of the sun because it was one of the largest events we'd ever seen, and we're projecting it onto the Earth to see what would actually happen if that event hit the Earth. So this is an event that didn't in fact hit the Earth, but if it had, we wanted to see what would happen. So notice here, right about here is where satellites in low Earth orbit sit. And you see they sit inside the magnetic field until that thing hits and pushes it all, and all of a sudden spacecraft which were sitting inside the magnetic field are now outside the magnetic field because all this stuff coming off the sun pushes it and is pushing the atmosphere and the magnetic structure of the Earth away from the sun. So this is a very extreme event. So let me show you a real example of space weather. Okay. March 7th, 2012. Keep an eye right there. So there was a flare. Here it is again. There's actually two flares. 1 and 2. You see all that stuff moving? That's material being blasted away. You can see the magnetic fields are actually wiggling. Those loops are actually wiggling. So that is, the flare is that flash of light, and it is throwing away, it's spitting, the sun is spitting out billions of tons of material. Now it's very difficult to see that from this perspective, to see that material leaving the sun. So what do? We actually create an artificial eclipse. So we take a telescope that looks at the sun in white light, in visible light, and we put a disk in front of the telescope to block out the bright sun, disk of the sun. Because what's happening during an eclipse, the disk of the sun is 1,000,000 times brighter than that wispy structure you saw during a total solar eclipse. So when the moon blocks the disk of the sun out, it's allowing us to see things that are 1,000,000 times fainter than the surface. It's just like looking at a bright light. If there's a little dim light next to it, you're not going to see it unless you put your hand up in front and sort of block it out. So we're going to do that. Now, the sun is actually in this little circle here. The reason being, we can't make an eclipse as good as the moon and sun system can. So we can't get the eclipse to block all the way down to the surface of the sun. So that's why this disk blocking the sun out is actually much bigger than the sun. But you'll see there's a wispy structure that came. There's this kind of smoke ring-like thing. That's the coronal mass ejection, or the CME. But then remember, that's pushing all this stuff in front of it. Particles. Super, super high energy particles traveling close to the speed of light. Well, you see all the snow? That's the particles hitting the camera, hitting the CCD. This camera has a CCD which is almost identical to what's in your cell phone or your digital camera. And when those high energy particles travel through that CCD, they leave these little tracks because they're depositing energy. And so that's the snow you're seeing. So this is actually a really big event. That's a lot of snow. That's a very, very huge particle event. Now, why do we care about that? If you're an astronaut in space, those particles, that's a blast of radiation. When you're on Earth, we are very well protected by not just the magnetic field of the Earth, but actually more importantly, the atmosphere. We live in a very thick atmosphere. It doesn't feel very thick, but there's a lot of atmosphere between us and space. And it stops all of those particles. Unless you're on top of a mountain or traveling in an airplane, you can't really measure much of these type of particles. They don't make it to the ground. But if you're an astronaut, and if you're out in the ISS or even traveling to the moon, then you're no longer protected. And even worse, if you're traveling to Mars, the moon is even sometimes protected by the magnetic field of the Earth, because sometimes the moon actually orbits in the magnetic field of the Earth. So it just so happens that in 1972, between the last two Apollo missions, there was a solar storm that produced the largest particle storm like this, all the snow, that we've ever recorded. So if either of those Apollo missions if the second to last one had gone a little bit later, or the last one had gone a little bit earlier, on a scale of about a month, astronauts would have been traveling to the moon, and a storm 10 times or more from this would have hit them. And they probably would have gotten a lethal dose of radiation, because they're not particularly protected in literally the tin can they were flying into the moon. So that's a really critical aspect, and that is one of the biggest challenges of traveling especially to some place like Mars. Now, when you go to Mars, Mars doesn't have a magnetic field, but it also has an extremely thin atmosphere. to put that in perspective, the atmosphere of Mars is about as thick as our atmosphere at 100,000 feet, higher than any of the commercial airplanes fly. If you've seen the movie The Martian, which is actually pretty good, there's a lot that's really quite accurate in it. The one thing that's not accurate in it is the storm. You could barely blow a tissue over with with Mars because the atmosphere is so thin. There's no pressure there, much less a spaceship or a rocket. But because there is no atmosphere, that means you are almost unprotected from these particles. So that would mean that you need to build your enclosure either underground, or you have to have materials that are thick enough to protect you from it. So this is one of the biggest challenges of traveling in space. The environment is quite harsh, and the biggest issue are these particles. Now, I'm going to talk a little bit more about some of the other types of and aspects of space weather, in particular how it impacts our technology. But in terms of flying through the solar system, these particle events are really the most critical part of space weather that we have to pay attention to. And this is the biggest challenge that we have going to a place like Mars. And for the moon also, it's still a huge challenge, but especially Mars. Because really it's the long-term exposure to radiation that is an issue. Now, one of the things I'm not going to go into, but there is another aspect to it. Our solar system is filled with particles from outside the solar system called cosmic rays. So huge explosions that happen around the galaxy called supernova, stars exploding. They create particles even more energetic than this. They're incredibly powerful explosions. And so those particles are everywhere, and they actually make it into the solar system through the magnetic field of the sun. But they are somewhat deflected by that. So when the sun is really active, these cosmic rays are actually less of them. The sun actually pushes. So when that heliosphere I showed you pushes outward, it actually pushes these cosmic rays out and away from the solar system. And as the sun gets quieter and that heliosphere shrinks, more cosmic rays get in. So when solar activity is low, cosmic rays are high. And we actually see, if you look at the sunspots and cosmic rays, they're exactly opposite each other. So that's the other challenge that I'm not going to talk about in any detail here, but that's the other part of traveling. It actually may turn out, strangely enough, that traveling during high solar activity may be better in the long run, because it's really the long-term exposure that's the issue. But these are still a problem. The other part of this, you see all those particles are hitting the telescope and leaving all the snow in there. Well, those particles also do the same kind of thing to electronics. They're traveling through memory. So one of the biggest issues is when one of those particles travels through a piece of memory, solid-state memory. So remember, we work in what's called binary, zeros and ones. All of our computers are using zeros and ones to carry information. And if one of those particles travels through, if it has enough energy, it can actually flip, turn a 0 into a 1 or a 1 into a 0. You've got a whole bunch of those. They make up an instruction that tells the telescope, take a picture, stay on, turn off, or tells a spacecraft, keep going forward, go to the left, go to the right. There are all these commands inside the computer that are made up of these zeros and ones. So you've got this command, and all of a sudden, a 0 changes to a 1. A spacecraft has all of a sudden been told, oh, turn off your engines, shut off life support, or something like that. I mean, so fortunately, it's not quite, it's a little more complicated than that, but that is a problem. So this is the other challenge when we go out into this harsh environment, is that we have to deal with this. And so we have to do all kinds of things like use software to make corrections. But when there's a really big storm, one of the things we have to do for our spacecraft is we actually turn them off. We basically put them in a safe mode. It's sort of like there's a thunderstorm coming, there's lightning, so you unplug your stereo or your TV so that if lightning hits, it doesn't overload it. We sort of do something similar to that. Basically put them in a safe mode so that these things don't have an impact. Here's another example. This is just another coronagraph showing you a slightly different perspective. Actually, there's a slight, you'll see the sun actually disappear. So I've actually overlaid an image of the sun on top of the coronagraph. There actually is an eclipse of the moon, and you can see if you look at it closely, you see the disk in the center all of a sudden gets black for a second. You have to, if you blink, you'll miss it. And this is one of the impacts of that storm. We had an amazing aurora all over the northern U.S., Michigan, Scandinavia. So there's some incredible aurora. But I'm going to show you really quickly what are some of the things we have to think about for space weather. So remember that all of this stuff that's happening is, again, it's electromagnetic. All of that material is plasma, which responds to electricity and magnetism, and it's carrying magnetic fields with it. So all of the phenomena that we're talking about is electromagnetic in nature. And so what does that mean? That means that it impacts technology. Okay. So a couple of things happen. So I mentioned those particles. The flare and the CME create those high energy particles you saw in the camera. Those impact spacecraft. They can damage electronics. There should be an astronaut floating around up here who would also be in danger. The other thing is that when you saw that model of the magnetosphere and this big blast hit it and it starts wiggling like this and everything starts moving, magnetic fields, when they move quickly, they create electrical currents. That's the physics behind generators and motors. You're moving a magnetic field very quickly, it generates electricity. Well, that happens in the outer atmosphere of the Earth. So there are currents that are generated up here. Now those currents also give us the aurora. They help to create accelerate the particles that give us the aurora. But it impacts communications. It disrupts GPS. It doesn't necessarily stop GPS, but it makes it less accurate. So if your GPS is telling you something is right here, the accuracy could be 10 times worse, and it could actually be, a couple of meters or even a couple of kilometers away. That may not be as big a deal for us, but these days we have farming that uses automated tractors that are running on GPS. We even have, this is crazy, I talked to a friend of mine who drives trucks. We even have people who drive trucks around dangerous mountains in bad weather using GPS. But we drill in the ocean for oil or things like that, doing even complicated construction. We use GPS for where things are. So that's a huge issue. It impacts communications on airplanes. One of the issues is airplanes can't be out of contact for less than somewhere on a scale of minutes when they're talking when it's talking to various airports. These storms, these currents, they're generated closer to the pole. So the magnetic fields go from pole to pole. So they go like this in this loop. When they come into the North Pole or the South Pole, that's where the magnetic field is weakest. And that's where the storms are the strongest. That's why we see aurora mostly near the North and South Pole. As a storm becomes stronger, we see these aurora move farther and farther closer to the equator. The storms are actually moving down the equator. That's what's happening. But if you're in an airplane and you're traveling from DC to Hong Kong, you want to travel over the poles. That's the shortest distance. But you can't travel over the poles if the communications are out because of a solar storm. So they have to travel around instead, which means that they spend a lot more fuel and a lot more money and a lot more time. So that's an issue for them. Also, if you're traveling as a pilot or an airline attendant for long periods of time over many years, you are exposed to more radiation because you're higher up. So that's an issue too. They don't want people to be traveling through the poles during a storm, one of those particle storms. And then one of the other issues is these currents are generated up in the atmosphere. They're also generated down on the ground. Because when currents run near a transmission line, okay, near a conductor, in this case, let's say between two electrical poles that are a kilometer apart. That's a long transmission line. That actually picks up those currents, and currents are generated in that. If those currents are strong enough, and this is actually much more analogous to the storm hitting your house, those currents can overload transformers, and they can take out power grids. And we've seen this happen. 1989, we had the entire Quebec power grid went out. And there have been other storms that have hit, generally, mostly communities in places like Sweden or Norway or something like that, because they're close to the poles. But if they're strong enough, they can reach farther south, and they can impact us. So that's another area that we have to be concerned on. Now, one thing to think about is that the good thing is that all of these industries are well aware of this. So they pay close attention to the weather report when it comes to space weather. And they take certain actions. As I said, they reroute planes, or they may change transformer settings and things like that. So it's something that they do pay close attention to. Now, I'm going to quickly go through a few things just to show you. So what do we do to keep an eye on the space weather? How do we do this? How do we keep an eye on that? Well, it turns out we have a huge fleet of spacecraft. We have 18 missions just in heliophysics, the study of the sun and its impact. Just in heliophysics, we have 18 missions that study all of these different aspects of what comes off the sun, what's traveling through space, and what reaches Earth. But as I mentioned, for NASA, we're also interested in all the other planets. So we put instruments on even things like Juno, which has just reached Jupiter, or New Horizon, which recently, last year, passed Pluto. All of them measure space weather phenomena as they're traveling through the solar system. Now, this is just the spacecraft that are around the Earth. This elongated structure is the magnetosphere. So again, the sun is now over here, and it's pulling this big, long structure back. But these are all of the different spacecraft that we have that are looking at that. And when we have all that data, we actually make... So here's just an example. There's a big storm that we measured. This actually went off the side of the sun because we have spacecraft around the sun. We have spacecraft on the back side of the sun. And we're able to see things that happen everywhere on the sun, not just stuff that goes to Earth. So you can see this was a really big event. See how much snow there was there? This was the biggest event ever recorded with modern spacecraft. And so we actually put that into a computer model with real physics. And just like we have a hurricane tracking, just like we track hurricanes to figure out where they're going to, how strong are they going to be, where are they going to make landfall, when are they going to make landfall, we do the same thing with solar storms. So there's one, there's the Earth, there's the sun. Now wait for it. There's the one you just saw. It traveled off this way. So there's a couple of smaller ones. There's Mars. That was the spacecraft stereo. There's a stereo here and a stereo here that are actually seeing the sun, not just from head on. So just to let you know, our generation, all of us, are the first humans to be able to see the entire sun at once. Because we have spacecraft everywhere, we actually see the sun, all of it, at one time. We don't just see the part that's facing us. And that's the first time that's ever happened. And so, as I mentioned, we do space weather forecasting for all the way out to Pluto. So here's New Horizon. So when the New Horizon mission was getting close to Pluto, they contacted the NASA space weather forecasters and said, all right, we want you to give us 6 months of all the stuff that's coming off the sun so we know what we should expect out here. Because we have instruments, but we have no idea. So it's like being somewhere and actually having rain gauges and things like that on your car, but you don't actually have you don't actually have the weather channel and the radar maps to know what's happening where you are. So you call somebody and say, hey, can you tell me what it's going to be like where I am? And so that's what they did. And so we make these kinds of forecasts that are just like a hurricane forecast for the entire solar system to know what's happening everywhere. So I want to end, this is actually a kind of a cool, this is just to show you, it's a little bit hard to see, it's kind of dim, but just to show you how dynamic the aurora is. So this is on a scale of tens of minutes. So it's moving pretty fast. But I want to end with one last thing. So I hope everyone gets a chance to experience this. Next year, 2017, August 21st, there will be a total solar eclipse. And that path of totality, which is about 60 miles wide, is going to start here in Oregon and travel down through South Carolina. Now we're going to be over here, we're going to see about 85% of a partial eclipse. 85% of the sun will be covered. But this is the first time we've had a total solar eclipse since the late 70s in the U.S. It's the first time we've had one that's gone across the entire U.S. since the early 1900s. The next time this will happen, that it's going to go all the way across the U.S., will be 2045. We will have another total solar eclipse that's going to start here and move like this in 2024.
Will we get totality from the 2024 one?
We are not going to get totality. We're again going to be really close, but it'll be easier for us. It's going to go like this, I think.
Okay.
So you can drive just up in northern Pennsylvania, I think. The interesting thing is that this totality in 2024 passes over the one that's happening next year. But I highly recommend, if you can take the time, to travel somewhere along this line, because you will not be disappointed. So if you want more information about this, go to eclipse2017.nasa.gov. But this is a really spectacular event, and I hope everyone gets to participate. And even if you can't go, there are going to be broadcasts from numerous folks, including NASA, but also, for example, Exploratorium in San Francisco. Other organizations are going to have live broadcasts and webcasts from all over the country. Now, anywhere along here, you will see totality for just over two minutes, roughly about 2.5 minutes, which doesn't seem like that long, but it actually is pretty long. It will be almost like night. It's an amazing experience. So I hope everybody gets a chance to take a look and try it out. So at this point, I want to end it and open up the floor for questions.
Yay! Well, first of all, in case anyone has to leave, thank you very much, Dr. Jones. And we will take questions. We could go on and on until they throw us out.
In the very back of the room, gentleman had a question.
2 questions.
Okay.
Very basic and one more abstract. Basic question. How would you specifically define the word field? F-I-E-L-D. Field.
How do you specifically define field in physics? Okay.
Second question. What is a Wolf-Rayet star?
What is a Wolf-Rayet star? Okay.
Okay? And I have a question backing that up. Go ahead.
Okay. Well, a field is, it's something that, let's see, this is a tough one.
No tough questions.
It describes a field. Yeah, a field describes some phenomena that is continuous. That is, it has every point. You can pick any point, and that field describes the strength of this phenomenon at that point, like magnetic field, electric field. But it's a continuous structure that defines some sort of force or quantity, flow of fluid, something like that. Wolf-Rayet star is my astronomy is a little rusty on this. I believe a Wolf-Rayet star is a young, very, very, very young active star. But I honestly don't remember. I'll have to look it up. I'm a little rusty on my stellar physics.
Are unfamiliar with Wolf-Rayet 104?
Well, that's from Star Trek.
Let's give somebody else a chance, please.
From a couple of astronomers in Australia. Okay.
Anybody can come up later and ask a few more questions.
Okay.
He's got to leave, so.
Go ahead.
About what time of day, Eastern Daylight Time, might this solar eclipse happen on August 21st? So you can put it on our calendar.
Yeah, so it starts, let's see, on the West Coast it starts around 10:30. You know what, I've got a little thing here, a little brochure that actually has the details. Let me pull it out. So let's see. Well, Central Time, for example, in Alabama, it's around noon. So it's going to be just about 1:30, I think, around here. Yeah. So it's going to go on for several hours, starting over on the West Coast. But if you go to eclipse2017.nasa.gov, you can get more details about that. And we have these maps too. So yes, sir.
In terms of the effects on astronauts who are outside of the perspective sphere of the Earth, I know there's been specific studies on the astronauts in the space station for long periods as to the effects of gravity, more biological types. Have there been any actual studies of the effects of space weather in general, or the increased radiation on them? Have there been any increased incidence of cancer? Or
There have. Well, all of the astronauts, for example, wear radiation badges because they're basically considered radiation workers, just like many airline workers are considered radiation workers. So they do monitor that. They do have various kinds of equipment to monitor as a proxy for humans. I don't know what the long-term studies are on ISS astronauts, but I do know that there's been a lot of studies recently related to Apollo astronauts, and they do have, it's my understanding there's a statistically significant increase in cancer and impact amongst Apollo astronauts. And they, of course, are exposed to the most radiation, more so than ISS, because ISS still gets some of the magnetic field protection, and the materials are better now. But I do know this is an active area of research, and there's a group, for example, at Johnson Space Center in Houston that actively works with the NASA forecasters, but they study the impact specifically for astronauts.
So just as a quick follow-up, if you look at that effect and the gravity effects and all the rest, does it make you, as a NASA scientist, does it make you wonder if talk about increasing manned flights or starting manned flights to Mars, if this is really a feasible idea?
It does. I mean, I'm not an expert on it, so I certainly don't speak from the NASA point of view. But yeah, it worries me. I mean, it is a huge issue. We do know that astronauts experience anywhere from 10 to more times the normal radiation levels. I mean, everybody experiences radiation all the time, and there's a normal background radiation. But astronauts certainly get significantly higher, and they know that. They're well aware of that. But yeah, it's going to be really, really harsh on a 9-month journey to Mars with cosmic rays. Not even necessarily the solar aspect, but just the continuous amount of cosmic rays. Because again, these sorts of things were not really, the issues is not as much acute, short-term, huge impacts, which is certainly still a problem. It's really that long-term, because the way radiation is measured, it's your cumulative dose over time. Because the same thing with pilots and with astronauts, they have a limit as to how much radiation they can get, and they will be grounded, and many have been grounded after they have reached that threshold. So they're gonna have to change those thresholds for Mars, because it's going to be much, much different. Yes, sir.
Given current measurements of solar activity on the surface of the sun is it possible to predict solar flares? And if so, how far in advance and with what kind of temporal resolution?
Okay, so the question is, are we able to predict solar flares and with what kind of resolution, timescale resolution? That's a great question. That's a really, really, really hard problem. Right now, we are only able to forecast solar flares on a statistical basis about the same as how we forecast precipitation percentages. So the way right now precipitation, when you see 80%, is that they look at equivalent conditions in the same location over time, over a certain amount of time, and say 8 out of 10 times when the day was like today, it rained, so there's 80% chance it's going to rain. And that's really about the best we can do with solar flares. We look at the sunspots and the structure of the sunspots and the magnetic field strengths, and we look at that particular type of sunspot configuration, and we look at past examples of that over multiple solar cycles, and we say, well, 8 out of 10 times we saw this particular shaped sunspot with this magnetic field configuration, and it produced so many flares of a certain size. And that's the way the percentages are done. So that's it's not a really very strong way to do it, because we're not able to currently do it based on the physics. I mean, ideally, that's what you want to be able to do. You want to be able to really look at the physics and say, we measure these physical parameters, and we can give you some sort of robust estimate of what's the probability of a flare. Right now, for example, the best measure of whether we're going to have a flare is if we already had one. Yeah, so it's a tough problem, and unfortunately I don't really have a very good answer because there isn't one. Yeah. Yes, ma'am.
Is it possible that we can feel the sunspot explosion?
As far as we've been able to, now you will see in different types of literature, and folks will say, well, you know, I'm affected by solar activity, blah blah blah. As far as we can tell, no, because one of the things is we are, again, fortunately very well protected by our atmosphere and our magnetic field. The thing about physics, when you talk about impacts, I mean, all honestly, almost everything affects everything else to some degree, but how much? And is it at all significant? And that's really the way physics works. I mean, if I have a magnet across that room, like a small bar magnet, there's a magnetic field here from that magnet across the room. But it will be extremely, extremely weak. And probably I will not be able to measure it. But I can tell you, based on what I know about physics, there is a magnetic field here from that magnetic field across the room. But there's also magnetic fields from everything else around me that's being produced that are probably significantly stronger than that. And so, more than likely, even though there's a field here, it really isn't affecting me, not in any sort of measurable way. And there's the same sort of thing with space weather impact. And as space weather becomes sort of more popular and in the public eye, I do hear a lot more about that, about the impact to all sorts of physical aspects, and there just really is no evidence that that's the case. I would be much more worried about, you know, walking by a hospital with a MRI machine than I would about the sun in terms of magnetic fields and that sort of stuff. Yes, ma'am.
Has anybody ever worked on at NASA if they had to reignite the sun if it went out?
Oh, that's a cool question. So has anybody ever worked if they had to reignite the sun? I don't know. I mean, I've certainly, being a science fiction fan, have seen lots of cool stuff about that. I don't know if anybody would think about it too much, because I think most people would sort of feel like, well, if we had to reignite the sun, it would mean the sun was out, and if the sun was out, we'd really be in bad shape.
Yeah.
So probably most people who've thought about that first thought that if that was the situation, I wouldn't really be here, so there really wouldn't be much I could do about it. But I think that's a cool question.
Well, thanks again. I guess we better stop, and if you want to come up, he's got a few more minutes before he has to get to a meeting. Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.